Okay, last time we talked about the binomial distribution, and this particular distribution allowed us to answer questions that had a format like this. So if we had a number of trials, a sequence of trials where we could have either success or failure, and these trials are all independent of each other. That is, the outcome of one doesn't affect the other. So if we can frame the problem in terms of a sequence of trials that are independent and where each one succeeds or fails, uh, and we also have a probability, which is the probability of success for each of those trials. So for each trial. And an important assumption is that this probability doesn't change from trial to trial. And then finally, we had, of course, the number that we're asking about. So this is just the number of successes for this given and fixed number of trials, the number of successes. Okay, so what the probability mass function for the binomial distribution gives us is the probability that x is going to be equal to this number of successes given a certain number of trials and a certain probability of success per trial. And we saw how that was equal to this, that this was the formula we used to calculate that. So if we take a look at this, we see, so that there's our x, this was our number of trials, there's our probability, and we can just plug everything in here, and what this gives us back is a probability. Okay, so that's what a probability mass function, and so every distribution is going to have a probability mass function, that is every discrete probability distribution, and that the function, the purpose of a PMF is to give you back a probability given x, and then the distribution itself has certain parameters here. Okay, so, and remember that in addition to the PMF, so we can use this PMF to solve problems like this. Okay, so what's the probability that x is going to be exactly 3, for example? Okay, and we saw that that's what we use this one for. So this is exactly. So when we're looking for the probability of one particular value, we can apply this formula here. And we saw that that formula is this one in your calculator. So the Binomial PDF. So this this PDF, these letters here actually they stand for probability distribution function. Okay. So when we get to continuous probability distributions, we're going to have something called a density. But this D in this context doesn't actually refer to a density. And so when we are looking for a particular exact value, we use the Binomial PDF, probability distribution function. And we saw also that this had a cognate over here in Excel. So this first one here is the same as this. So we use the binomial dist function in Excel. And so this is saying, okay, so for a binomial distribution with, we're curious about 9 successes out of 10 trials with this probability. And when we put this false here, we are looking for exactly 9. So exactly 9. Okay, so we also saw that if we want to do something else, and we weren't just interested in an exact value, but we were curious about, well, what's the probability that x is going to be less than or equal to, say, 9? And we saw that this is really more like a real world question that you would have. You're seldom interested in just one exact value, but you might be interested in a range of values for something like capacity planning or something. So if we have this situation where we're not, we're interested in a certain range, particularly less than or equal to, then we use the CDF, which is here, and this stands for cumulative distribution function. Now later on we're going to see that there's something called the probability density function and so forth. But for now we just want to note that these D's stand for just the general distribution. So the probability and then the cumulative. So the cumulative is for questions like these, and we saw that Excel, to do the same thing in Excel, we use this function. So binom dist, and then the same parameters, except here we say true. And so this is the so-called cumulative parameter. So you're just stating, well, do you want the cumulative distribution function or just the regular probability distribution function? Okay, so if you look through your calculator under the distributions, you'll see that there's a very nice parallel here where we've got the binomial PDF and the binomial CDF. You'll also see, let's go ahead and take a look at that. So, there's going to be the normal PDF and the normal CDF. We got the chi-square PDF, the chi-square CDF. So they come in these pairs, FPDF, FCDF. So that principle is going to apply to all of these cases where you use the PDF for a particular value and the CDF for some kind of cumulative value of less than or equal to. And then, of course, if you want, let's say in this case, to, if you need to do greater than, let's say you're interested in greater than or equal to, let's say x is greater than or equal to 6. Now, how do we do this? Because these functions give us less than or equal to. Well, this is going to be the same thing as 1 minus the probability that x is less than or equal to 5, right? Because this is a discrete probability distribution, to be less than 6, so the opposite of greater than or equal to is less than. So to be less than 6 is the same as being less than or equal to 5. So in order to do probability greater than or equal to 6, we do 1 minus probability that x is less than or equal to 5. Okay, so there's a review of the binomial distribution and how we used it. So let's say we have another realistic problem like this one. So if historically 5 customers arrive per hour, what is the probability of 7 arriving in any given hour? Okay, well, so far we've only, clearly this is a probability question. Okay, so we're looking for a probability. And we know that because customers are counts, right? This is a count. So we know that it has to be a discrete. So count implies discrete. And so far the only probability distribution we've looked at that is discrete is the binomial. So let's see if we can cram this problem into a binomial. Let's see how far we get with that. So we've got, we're asking about 7. Okay, so we've got our x. We got x is equal to 7. Okay, we want to know the probability of 7. Okay, now what else do we need for a binomial? Well, we're going to need a probability, consistent probability, and we're going to need an n. Okay, now these we don't have, but let's see if we can be creative here. So what do we have? Well, we know that on average 7 arrive each hour. So we know that on average 5 arrive per hour. So in our old terminology, we can say, okay, well, our expected value then is equal to 5. Okay, and so this is the usual rate. So 5 customers per hour. Okay, so in statistics, it's customary to denote some kind of rate with the Greek letter lambda, Lambda, lambda. Okay, so here's what we do have. We don't have a probability or a number of trials, but we do have a rate. We have an expected value. So if 5 arrive per hour, then we know that we can expect 5 to arrive per hour. There will be more or less, but that's our expected value. So we can just say we've got a lambda of 5. Okay. Now remember that we're treating this as a binomial problem. So in a binomial distribution, the expected value is equal to n times pi. Okay. So for example, if your probability of succeeding at each basket attempt is 0.5 and you try 10, then you can expect 5 successes. Okay, so it's just a product of n and pi. So we can say, okay, well, we've got our expected value. We know it's 5. Just to keep it general, we're going to just call that lambda. And we know that it's equal to the product of n and pi. So let's just do a little bit of algebra here. And we say, okay, well, that means that lambda over n is equal to pi. Okay, well, let's just use that then. Okay, so we can say, okay, so our probability is equal to lambda over n. And so, of course, this begs the question, well, we don't have n. What do we do about this n? Well, let's think about what what we're trying to do here. We're trying to cast this problem into a binomial. And so how are we defining these things? So let's just say, well, let's say that we're going to call n just like every person in the world. Okay, so n is every single person, and so we're asking about arrivals per hour. So we're going to say, okay, well, what's the probability of this particular person arriving in a given hour? Okay, so you can say, well, that's going to be very low, obviously, but n is going to be very large. So what can we do? We already know that we can describe probability in terms of n. How should we treat n here? Well, we know that n has to be large. So let's let n be as large as it can possibly get, that is infinity. So we're going to look at the limit as n goes to infinity. Okay? So in that case, then we can now plug these things into the binomial PMF and see what happens. So with that binomial probability mass function, remember we had probability that x is equal to x given n and pi are equal to, so we had n factorial over x factorial n minus x factorial, and then pi to the x, and then times 1 minus pi to the n minus x. Okay, but now we're going to be plugging these things in here. So our n and pi is given are these things. So what we actually have here, and I'll move this equals over a little bit, is going to be, okay, so the limit as n goes to infinity of this, okay, so since we're doing a limit here, we can just put this in like this. Let's not substitute. Well, we can do the limit of this and then substitute in the pi's over here. So limit n factorial over x factorial n minus x factorial. Okay, so now we got pi to the x here, so this is our pi. So this is going to be lambda over n to the x, and it's 7 here, but we'll keep it general. And then times 1 minus lambda over n to the n minus x. Okay, so in solving limits, you may remember this from calculus, we can pull constants out. So anything that doesn't depend on n, we can pull out, and then we can do some rearrangements and so forth. But I'm going to, if you'd like to see all of the intermediate steps, you can probably find that. I can recommend a source for it. But I'm going to skip a step and then just show you that when we pull out the constants and rearrange some things, we wind up with something that looks like this. So we have, and go ahead and write it out. So probability that x is equal to x is going to be, we're going to have that lambda pulled out, lambda to the x, and then it's going to be, once again, we've got this limit as n goes to infinity of 1 plus 1 over n to the n to the minus lambda, and then this is all going to be over x factorial. Okay, now this gets us a little bit closer, but this probably looks pretty impenetrable. But notice that we have a limit here that turns out to be very well defined, and we know what this converges to. So this function right here, if we were to take 1 plus 1 over n to the n, what we see that as n gets larger, I mean the whole thing gets larger, so it just keeps growing, but we see because it's adding 1 over n that it's adding smaller and smaller amounts as it gets larger. So it's always increasing, it's monotonically increasing, but it's increasing at a decreasing rate. Okay, so the question is, well, if this is converging to some value, what is it converging to? Well, let's, we can solve it or we can use definitions, but sometimes I like to just go and see what happens. So I've got this function put into Mathematica here, and I'm just going to plot it for different values. So notice that this is just 1 plus 1 over n to the n, which is just this. And then I'm going to start plotting it and then see what happens as I take n. What this is saying is, okay, plot from n from 1 up to 10. Okay, so I'll do that. Okay, and I see that as predicted, the function is growing, but at a decreasing rate. Okay, so the first derivative is positive, second derivative is negative. Okay, so if I make this 100, okay, once again I see that it seems to be leveling off here at like 2.7 somewhere. Take it up to 1,000. Okay, once again I see, okay, so it's leveling off at 2.71 something. Let's take it, and let's just keep on going up. Let's make it larger and larger. We make it 10,000. So if n is now 10,000, we see that it's getting very close to 2.718. And then we could take it up to 100,000, take it up to 1,000,000, and we see that it just keeps getting closer and closer to 2.718. Let's even go up to 10 million. So it's 2.71828. Well, it turns out this is one of these magical constants that crops up in mathematics. The fact is this converges to an irrational number. So this is going to get closer and closer and closer, but never quite reach a certain number that is somewhere around 2.718. 2.7. This is really messy. So this is equal to somewhere around 2.718. And the name for this constant in here is E. So some of you may recognize this from finance as what happens with compound interest. So you have to use the constant e to calculate compound interest. But for our purposes, just know that the way this came about was we wound up with this expression, which we know is equal to e as n goes to infinity. Okay, so then the final equation is our lambda, which remember was our rate, to the x, and then this is e to the minus lambda all over x factorial. Okay, so this is our probability mass function. Okay, so given an x, and if we already know the rate, so maybe I can even write that in there. So this should be, so probability of x having been given a rate, a lambda, then this would give us the probability of observing x. Okay, so the probability that this random variable is equal to a certain x given a certain lambda is equal to this. And this was discovered sometime in the 1800s by a Frenchman whose last name was Poisson. So that's pronounced Poisson. Poisson is close enough. I'd prefer not to hear Poisson or Poison, but Poisson is definitely acceptable. Permissible is close enough to the French. So this is what the formula looks like. Now I think my equation came out to be slightly reversed order, but multiplication is commutative, so we won't worry about that. So this is called the Poisson distribution formula. So now we have, in addition to binomial, we have a version of the binomial that allows us to answer questions that are where n is approaching infinity. And so this is what the Poisson gives us. Now, much like with binomial, where we had a certain number of key terms that allowed us to identify when a problem was a binomial problem, so that is the n trials, the certain number of successes, and the probability, the key terms for a Poisson distribution is going to be, we're looking for a certain number of events per, and then this is called area of opportunity. But this could be like events per unit of time, events per unit of space. Okay, so some kind of continuous quantity. So notice that we have, this is a discrete value, so number of events in a given unit of time. And so a lot of times the key word here is arrivals. And we're looking for, the number of customer arrivals, or the number of defects in a certain amount of space, the number of typos, per book or something like this. So the key there is that we're looking for a particular number of events in some kind of area, which can be either time or space. Okay, and lambda, as we said, was the expected number of events. Okay, so in our example, we were looking at customers per hour, right? And so we said lambda was equal to 5 customers per hour. So given that we have 5 per hour, what's the probability that there will be 7? Okay, and then E, I explained, is the base of the natural logarithm system. So it's a mathematical constant equal to 2.718. You don't really need to expand it like this. In fact, it goes on infinitely because it's irrational. But when you're calculating E, you'll notice that on your TI-84, it's just it's just here under 2, and then it's just under, right here. Okay, so that's saying e to something, and it's the inverse of the natural log function. Okay, But we're not going to mess with that too much. But okay, so let's go ahead and apply this to a problem then. I hope that the derivation helped you see how this came about, how this particular formula came about. But if not, then it's enough to simply know that the Poisson uh, is a way for us to determine the probabilities of a certain number of events per unit of time or space, given only a rate. Okay, so let's go ahead and see this in action. Okay, so we're back to our original problem. So if historically 5 customers arrive per hour, what is the probability of exactly 7 arriving in any given hour? Okay, so we've got our x here. We said that x is going to be equal to 7. And this 5 is our rate. So we've got a lambda equal to 5. Okay, so let's just go ahead and plug it into the Poisson PMF. So probability that x is going to be equal to 7, given that lambda is equal to 5, is going to be equal to 5 raised to the x, which is 7, okay, times e raised to the negative lambda, so lambda's 5, so it's e raised to the negative 5, and then this whole thing over x factorial, and x was 7, so over 7 factorial. Okay, so let's go ahead and see what the answer to this is then. So clear here. Now, one thing to remember when you're putting expressions into calculators is the operator precedence rules. So you want to be careful to group your expressions with parentheses so that you get the right answers. In this case, I can just kind of look and notice, okay, well, I know that because of operator precedence rules that these exponentiations are going to be done first. And then likewise, this factorial is going to be done first, as it should be. So if I just put it in, and then everything will be done in the correct order. So first the exponentiations, then the factorial, and then it will be doing this division. Okay. But if you're not sure, then you might want to try putting parentheses around a numerator. Okay. I've had students have trouble with that in the past. So let's go ahead and calculate this. So this is just going to be 5 raised to 7. Okay, and then to get out of this exponent, we just hit the right key. Times, actually, let me hit that. We'll go ahead and put the explicit times in there. Times e raised to the negative 5. Okay, and then we'll right key to get out of the exponent again. Divided by 7. And then remember, to get to that, we have to go math, and then over to probability, and then down to the exclamation point. And so we find that this probability is equal to 0.104. Okay, so 0.104. So the probability of having exactly 7 customers in a given hour, now that could be the first hour of the day, the 5th hour of the day, but any given hour, the probability of 7 arriving during that hour is about 10%. Okay, so that's how we apply the formula. And as usual, there's always a quick way. As long as you understand what the formula is and why we use it, then it's okay to go ahead and take some shortcuts. And so your calculator does give you a Poisson function, and much like with the binomial PDF versus CDF, we have a Poisson PDF, which would be just the thing for solving this exactly 7 problem. So let's go ahead and just use the distribution then and check to see that that answer coincides with what we got before. So we can just come down here to, so there's right below the binomials, there's this Poisson. So we'll take the PDF. Okay, so lambda, we said lambda was equal to 5. And the x we're looking for is 7. Okay, and so it gives us the same answer. It looks like even down to the decimal point. So it must just be doing this internally. Okay, so that's how we would do it in the calculator. So as always, I'm going to also show you how to do it in Excel. So if you had to guess, given how these things worked before, the parallelism, I think that you can probably guess that the way to do it is to is equals and then Poisson dist, okay? And this x is the number we're asking about, which in our case is 7. The mean, so it calls this lambda the mean. That is the average rate, the expected rate, the mean rate, all the same thing, is our lambda. So our mean is 5, and cumulative. So remember this, if we say false here, this is going to give us the PDF. So we'll say false, and we see that it is the same answer. Okay, so Poisson dist is the same as the Poisson PDF. Okay, now one more thing I want to show you since we're here in Excel is to think about what these numbers are telling us. Okay, so what I've done here is I've given I've made a sheet here where I can put in different lambdas so that I can see what happens with different x's. Okay, so in this case, so for example, you can see that in this cell, in this column, I'm calculating the Poisson distribution for this number of arrivals. So the probability of this number of arrivals given this mean, so this lambda, this average rate of arrivals, okay, and then putting in false for the PDF. So you can see that if my average rate of arrival is 0, that means the probability of 0 arrivals is 1. Okay, so if you average 0, that means that you're because this can't be negative, that you must never have any customers. Okay, so we see that the probability of 0 is 1. If we put in 1 here, we see that the given historically that we've had 1 customer per hour, this is the probability that in any given hour, this number of customers will show up. So we'll say, okay, well, if we get 1 per hour, then we see that the probability of nobody coming in that hour and the probability of 1 person coming that hour are approximately the same. But then it becomes much less likely. So these are the probabilities over here. It becomes much less likely as we get larger. Okay, and you can see if we have 1 customer per hour, the odds that in any given hour we're only going to have 5 is very small. It is 0.003. Okay, but as this goes up, we'll see that this distribution shifts over to the right. Okay, so what this is saying is if historically, if on average we expect 2 people to show up every hour, then the probability, the expected value is going to be like, 1 or 2, right? So if we get 2 people per hour, that means that 1 or 2 people in any given hour is highly probable. It's less likely that 0 are going to show up, and it's very unlikely that 7 are going to show up. But let's let's make this fairly large then. Let's say that historically we have 8 per hour. That what this distribution is telling us is that the probability of having 0 is very small. Okay, so that makes sense. If you're used to 8 per hour, the probability of 0 in any given hour is very small. But as we get closer to 8 here, these probabilities get larger so that, 7 or 8, very likely, 6 or 9, a little less likely, but also pretty likely to happen. You're less likely to get 10, and you're extremely unlikely to just get 1 or 0. Okay, so this kind of gives a visual of what exactly the Poisson distribution is telling us. Okay. Okay, so this this is the PMF for an exact value. So much like in the binomial, we have cases where we're not necessarily looking for a particular value. In fact, you can think about, well, the probability, the difference between 5 customers and 7 customers seems pretty trivial. And so to ask about the probability of 7, that doesn't seem like a very important question. But if you think about, well, okay, there might be some facility that expects 5,000 customers and they have to plan that way. Well, what's the probability that they're going to have 6,000? Well, probably not very large, but you might want to know what's the probability of more than 6,000. Now, that's a pretty key question. So we don't necessarily always want to ask about the exact values, so we need to go from that PDF to that CDF, the cumulative distribution function. Now, the Poisson distribution does have a CDF, but it's pretty involved. It's actually a lot more complicated than this, and we don't really need to worry about it as long as we know how to use the CDF function on the calculator or Excel. But we do know that there are cases where we want the CDF. Okay, so let's take a look at one of these. If historically 5 customers arrive per hour, what is the probability that 7 or fewer? Probability of 7 or fewer arriving in any given hour. Okay, so now we're dealing with a range. So we want to know probability of x being less than or equal to 7 given lambda equal to 5. Okay, and so I'm not going to write out the CDF, but we know because of this that we want to be using the Poisson CDF, and we're going to be using with a mean of 5 and an x of 7. Okay, so let's just do that then. So, okay, we'll clear that. Scroll down to the Poisson CDF. And now our lambda is 5. Our x value is 7. Okay, so 0.867. So equals 0.867. Okay, so notice that that's pretty high. And the reason for that is if you average 5, the probability of 7 or fewer, in fact, we can even look at this. So if we average 5, the probability of 7 or fewer is all these added together. So that's going to be, over 80% of the total probability mass. Okay, so nearly 90% chance of having 7 or fewer. Okay, so that you can see why something like this would be useful to know for planning. Okay, again, let's do it in Excel just for the sake of completion. So this time we'll just use the Poisson Vist. And once again, we're asking about 7. Our mean is 5. And this time we want cumulative equal to true. Okay, and at 0.867. So we get the same answer. Okay. So it doesn't matter which tool we use. They calculate it the same. Okay, so let's look at a slightly different case then. So if historically 5 customers arrive per hour, what's the probability of 6 or more arriving in any given hour? Okay, so now we're not asking a question about less than or equal to anymore. Probability less than or equal to whatever. We want to know the probability of x greater than or equal to 6. Okay, so we can recast this as a problem that we can solve. Well, 6 or more is going to be the complement of 5 or less, right? So we're going to do 1 minus the probability that x is going to be less than or equal to 5, right? Okay, so because these are discrete values, the probability of something being greater than or equal to 6 is 1 minus the probability of x being less than or equal to 5. Okay, so let's go ahead and solve that one then. Okay, so we're going to do 1 minus shot over here. Let's move this back. Stay over there. Okay. Poisson CDF for 5 and 5. Okay, so our 5 per hour, and we're curious about 5. Okay, and so that winds up being 0.384. Okay, so 2.384. Okay, so let's take a look at a slightly different problem. So instead of looking at number of events per area of time, we're going to look at a problem actually from the homework that is looking at a certain number of events per unit of space. So let's take a look at it. So the quality control manager of a cookie company is expecting a batch of chocolate chip cookies that has just been baked. If the production process is in control, the mean number of chip parts per cookie is 5. Okay, so we should immediately recognize that this, by giving us a mean number, we apparently already have a lambda. So we say lambda is 5. Okay, so how many cookies in a batch of 100 should the manager expect to discard if the company policy requires that all chocolate chip cookies sold have at least 3 chocolate chip parts? Okay, so go ahead and pause the video and see if you can figure out how to solve it using what you've learned so far. Okay, so our random variable, we'll define our random variable x as the number of chocolate chips in any given cookie. Okay, subject to a certain amount of randomness, just because the limitations of the machines dropping things. So okay, so that's our random variable x, and so how do we define what we throw away? What makes a bad cookie? Well, it's bad if x is less than or equal to 3, or less than or equal to 2, right? Because good means that it's greater than or equal to 3. So this means at least 3. So the opposite of this, because it's discrete, is less than or equal to 2. Okay, so if we're saying, okay, in a batch of 100, how many can we expect for there to have less than or equal to 2? And this is nothing more than the probability that x is going to be less than or equal to 2, given that lambda is equal to 5. Okay, so this is going to be a CDF. Let's go ahead and let's do it in Excel, just for a little variety here. So we're going to say this is going to be equal to the Poisson dist. Okay, and so we've got our x. We're curious about 2, and our mean is 5, and we want cumulative, so we'll say true. Okay, so 0.125. So the probability, so this is going to be equal to approximately 0.125. Okay, so if the probability, so remember that the probability goes from 0 to 1. So to convert this into a batch of 100, we can just multiply it by 100. So that means that we're going to have to throw away 12.5 cookies out of every 100. Okay, which probably means they need to recalibrate that, because that seems like a lot of waste. Okay, well, as always, I hope that helps, and please let me know if you have any questions.